Welcome back to Science Sizzle, the show where we bring you the stories that challenge our understanding of reality. Today, we're talking about a result that's making quantum physicists around the world raise their eyebrows, a violation of Bell's inequality without entanglement. For decades, Bell's inequality has been at the heart of quantum theory, and every violation we've seen involved entangled particles. But now, an international team of scientists says not necessarily. Joining us is Professor Xiaosong Ma from Nanjing University, who led this remarkable experiment. Professor, welcome.
Thank you. I'm excited to be here and share why this is such a significant result for quantum foundations and beyond.
All right, let's start with the basics. For our listeners who aren't physicists, why does Bell's inequality matter so much in the first place?
Great question. Bell's inequality is a test for something called local realism. The idea that the world is both local, meaning nothing can influence something faster than the speed of light, and real, meaning objects have definite properties even when we're not looking at them. If quantum mechanics was just weird math, Bell's test gives us a way to check if nature really works that way. And what decades of experiments have shown is that local realism fails. The universe does not behave classically, it's deeply quantum. But historically, every time we saw Bell's inequality broken, entanglement was the hero.
Right. Entanglement, the famous spooky action at a distance that Einstein couldn't accept. Two particles acting like one, no matter how far apart they are. So, what made you think it might be possible to break Bell's inequality without entanglement?
It started with a simple question. Is entanglement really the only way to get non-classical correlations? In quantum physics, there are other resources besides entanglement. One of them is quantum indistinguishability. If you set up a situation where particles are so similar and their paths are so perfectly aligned that you can't tell them apart, even in principle, they can interfere in ways that look very non-classical. We wondered, could that interference mimic or even achieve a Bell violation?
And the answer was yes?
Yes. What we did was use 4 photons in a carefully arranged interferometer. Imagine 4 photon sources arranged in pairs. 2 pump beams could create photon pairs in either one pair of sources or in another pair. We made sure the paths of these photons were absolutely identical. No clue existed about which source produced which photon. That path identity is the essence of indistinguishability. When you measure 4 photons arriving at specific detectors, you have no way of knowing which generation process they came from. This creates interference between 2 possible histories, and that interference was strong enough to violate Bell's inequality.
That's incredible, but some people listening might say, hold on, you started with entangled photons. How do we know this isn't just entanglement doing the heavy lifting?
Fair point. At the beginning, the photon pairs do have entanglement in momentum and frequency, but we deliberately destroyed that. We used single-mode fibers and narrow-band filters, which completely project out those correlations. So by the time we test Bell's inequality, there's virtually no usable entanglement left. What's driving the violation is the indistinguishability of the paths, not entanglement.
So what's the scorecard? How strong was your violation compared to the classic limit?
We measured a Bell parameter of about 2.275. The classical limit is 2, and quantum theory predicts a maximum of about 2.828 for ideal conditions. Our result is more than 4 standard deviations beyond the classical bound. Statistically, that's very strong evidence.
Let me just step back for a second. For decades, Bell's violations were synonymous with entanglement. Your result says, actually, no, they're not. That seems like a big conceptual shift.
It is. It forces us to think about what really makes quantum physics non-classical. Maybe it's not just entanglement. Maybe it's more fundamental features like superposition and indistinguishability. And that could have practical consequences.
Practical consequences, that's where I was going next. Does this have any real-world impact, or is this just a mind-bending experiment for theorists?
It's definitely mind-bending, but it's not just academic. In quantum technologies like secure communication and quantum computing, we focused a lot on entanglement as the key resource. But entanglement is fragile and hard to maintain. If indistinguishability can also create non-classical correlations, maybe we can build simpler systems that don't rely on entanglement but still beat classical limits. Imagine quantum networks that are easier to scale because they don't need long-distance entanglement distribution, or quantum imaging techniques that use this principle to enhance resolution without the usual complexity.
So this could open up a whole new toolbox for quantum engineers.
Exactly. It's early days, but it shows us that quantum weirdness can work in our favor in more ways than we thought. And that's the exciting part. Every time we peel back a layer, we find something new.
One last question. Does this settle the philosophical debate about reality that Einstein started?
I think it deepens it. Einstein said God does not play dice. Well, now we know that dice aren't just loaded, they can be indistinguishable. This result doesn't break quantum theory, it shows how rich and subtle it really is.
Professor Ma, this has been absolutely fascinating. Thank you for giving us a glimpse into the next frontier of quantum science.
Thank you. It's been a pleasure.
And to our listeners, the universe just got stranger, and that's a good thing. We'll see you next time on Science Sizzle.